Welcome students to the series of lectures of statistics, and in the series of lectures of statistics for CFA and FRM, we are into another series of lecture on probability distribution, and in probability distribution we completed the discrete probability distribution, and now we have entered into the discussion of continuous probability distribution. And in continuous probability distribution we are into the distribution. The name of the distribution is normal distribution. And in normal distribution, we completed two sessions, two lecture. The first was on the properties of normal distribution, and the second was on the introduction of the central limit theorem, which is the theorem behind the normal distribution. We discussed why everywhere, what is the rationale that everywhere you see normal distribution or normally distributed bell curve. So we discussed version 1, which was very simple and straightforward, and which was the core essence of the central limit theorem. The sum or average, the version 1 was the sum or average of the outcome of the ID variable tends to normality as n increases and n is greater than 30. So there are three important words. The first is ID variable, the second is sum or average, and the third is n is greater than 30. If all these three conditions are satisfied, then any distribution will approach normal distribution, tends to normal distribution. But the problem with this version is that this version is not written in your curriculum, but this is the thematic essence of all the version of central limit theorem. The version that is written in your curriculum is this. I'm reading it for you. Listen very carefully. It says that for simple random samples, for simple random sample of size n from a population which has a mean of mu and a variance of sigma square, the sampling distribution, very critical, the sampling distribution, not population distribution, the sampling distribution of the sample mean approaches normal distribution with a mean of mu and the variance of sigma square upon n as the sample size become large and greater than 30. Okay. So when you read it, then it is very difficult to understand the essence, what it is saying. So we'll try to help you understand the version 2 of central limit theorem. So let's see what is the version 2 of central limit theorem. So for the central limit theorem, first of all, for version 2, you have to take a population distribution. So this is your population. Okay. The circle is your population. Could be India population. So this circle is the complete population. It's not sample, it is population. You can also write it down, it is population. Now the population distribution has the center, which is the mean as mu. This mu could be anything. It could be 5, it could be 10, it could be 15, right? Assume you're interested in India population or Indian age, the population age. You're interested in that. So the mean could be like 35, 40, whatever could be the mean, right? The mean is mu, and the variance could be 5, 7, 10, 15, any number, right? So you have mean, which is mu, and the variance is sigma square. This is the population. Now, you don't know whether this population is normally distributed or not. You don't know. And you don't care about it, whether it is normally distributed or not. Important. You're not interested in population distribution. Okay. Now, what do? You start taking sample. So you took a sample, you took another sample, you took another sample. Okay. You keep on taking random sample. What sample? Random sample. The sample selection should be random. It should not have any logic. It should be completely random. Now assume the sample size is 35. Why I am taking the number 35? Because it is greater than 30. So I took a sample 35, 35, 35, 35 and randomly taking the sample of Indian population. And I'm interested in age. So I took the first sample. This is my first sample. I took the sample. I calculated the mean. My mean is x1 bar. Now this x1 bar could be anything. It could be 22 years or 23 years, 24 years. I don't know. X1 bar. Assume it came to 22. Okay. X, then you took the second sample. When you took the second sample, you got x2 bar. Now say x2 bar is 35 or 36, 37, doesn't matter. And there would be a variance of sample 1 and sample 2. The variance is s1 square and s2 square. Then you took third sample. The third sample mean is x3 bar and the variance is s3 square. Okay. This x3 bar could be like 40. Doesn't matter. The x1 bar was 22. Okay. The question is you're randomly taking the sample and calculating the sample mean. So what is this sample mean? What is this sample mean? What is this sample mean? And the sample mean, the first sample mean was 22. The question is if you take another sample, keep on taking other samples randomly, will you not get 22 next time? Yes, you will get 22 next time as a sample mean for another sample. It could be sample 57. You could get the sample mean as 22 for sample say 104, right? So it's not necessary that the 22 as a sample mean will occur for only one sample. It can occur for multiple samples. So the frequency of 22 is not 1. It could be 10, it could be 20, it could be 33, it could be 34, it could be 120, it could be million. You don't know because you can get 22 as the mean for another sample. Similarly for x2 bar, right? Now what you have to do? You have to plot the frequency of x1 bar, x2 bar, x3 bar, as in you're plotting the probability of sample mean. I'm repeating, you're plotting the frequency of sample mean or you're plotting the probability of sample mean. And you took the sample which is random. And if you plot it, so you plotted x1 bar, you took the frequency, x2 bar, you took the frequency, x3 bar, you took the frequency, x4 bar, you took the frequency, x5 bar, you took the frequency. And when you plot it, it will appear normal distribution. It will tend to normal distribution. And the most important thing is it will appear as normal distribution, which will have a mean equal to the population mean. If the population mean is 35, this distribution mean will be 35. Why? Because what will be the mean here? The mean of all the sample mean will be equal to population mean. You remember the discussion of moment one blue? Why mean is blue? Because mean of all the sample mean is equal to what? Population mean. Because that is the formula of mean summation of xi upon n. The formula is designed in a way that if you keep on taking the samples, all the exhaustive sample, if you calculate the mean of the sample and then you take the mean of the sample mean, that is going to be the population mean. The mean of the sample mean is going to be the population mean. It has to be because it is blue. Okay. But the variance is not going to be sigma square. The variance is going to be sigma square upon n. Now the question is not why the variance is sigma square upon n, or the question is not like why the mean of the sample mean is going to be the population mean. The critical question is how this can be normally distributed. Because there are three properties that got satisfied. The number one is sum or average. See, sum or average. What are you taking? The mean. What is mean? Mean is average. The sum or average of ID variable. Where is ID variable? These are random sample. They are independent and identical samples. Why they are independent? Because you're choosing it randomly. Why they are identical? Because the sample size is what? 35. Okay, the sample size is fixed and it is on what? It is on Indian population age. So it is independent and identical, randomly choosing. That's why it is independent. Identical, because the sample size is fixed 35, and you're choosing what? Indian population, not Indian population and then Chinese population. No, only Indian population. So independent and identical. The third condition, n is greater than 30. The number of entity that you're adding to calculate the sample mean is what? 35, greater than 30. Because these three conditions got satisfied, that's why the sample mean distribution is following normal distribution. And very important point, the sample mean distribution, the distribution of the sample mean. What is the distribution of the sample mean? You're plotting the mean and the probability or the frequency associated to it. What you're plotting, the frequency or the probability associated to it. When you plot it, the name given to this distribution is called as sampling distribution. What distribution? Sampling distribution. What is a sampling distribution? Sampling distribution is a distribution where you plot the mean of the sample mean. Sampling distribution. It is not sample distribution. If you just plotted one distribution sample, one probability distribution for a given sample, say S1, that is a sample distribution. If you plot the sample distribution, then it means you took all the 35 entities, say the age is 2, 10, 12, and you write the probability of each age in this sample only. That is called a sample distribution. What is sampling distribution? Sampling distribution is that you're taking different samples, you're calculating the mean of different sample, and then you're plotting the mean frequency. What is mean frequency? The sample mean frequency. That is sampling distribution. And there is third distribution, which is a population distribution. This is what? Population distribution. If you plotted the exhaustive population of India and the frequency associated to each age, not sample, each age in the Indian population, then that is population distribution. So you need to know what is the difference between the population distribution, sampling distribution, and sample distribution. Sampling distribution is very critical because with that you will do hypothesis testing. And sampling distribution is also critical because that is written in your curriculum for version 2. It is saying sampling distribution approaches normal distribution if the sample size is greater than 30 and if you have taken random sample from the population. So let's read it again. It is saying you have to choose a random sample of size n. This n should be greater than 30 from any population which has a mean of mu and the variance of sigma square. And if you plot that sampling distribution, as in, what is sampling distribution? The distribution of sample mean. The sampling distribution of the sample mean, it will approach normal distribution with the same mean mu, because the mean of the sample mean is going to be the population mean, but the variance is not going to be sigma square. The variance is going to be sigma square upon n. N in our case is 35. And it will approach normal distribution. So this is the central limit theorem. Now, if you have understood the central limit theorem, again, the word which is important here to understand, it approaches normal distribution. It is never gonna be written anywhere that it will be normal distribution. And I want to explain this with the help of a data that is randomly generated. Okay, so we'll look this Excel sheet and try to understand this version 2, the version 2 with the help of the data. Okay. So let's go to our Excel sheet. So this is your Excel sheet, and understand and try to understand that I'm just trying to help you give the intuition of approaches normal distribution. Okay. So what we need, step 1, we need population. From the population, we'll randomly select the sample. That is step 2. Step 3 is we'll calculate the mean. And then after step 3, when we calculate the mean, we'll plot the mean distribution. Okay. And we'll also try to see whether that distribution mean is equal to population mean or not. And if it is not equal to population mean, then what is the difference? And will it approach to the population mean? Question 1. The second is the population variance. We'll calculate the population variance. It will come to, say, any number. And then what we'll do, we'll try to calculate the variance of that sampling distribution and try to see if the sampling distribution variance is equal to population variance upon n. We'll try to test it. Okay. what will happen at the end when we'll discuss this, what will happen at the end, every time it will try to approach normal distribution. Every time the sampling distribution mean will try to approach the population mean, will but never be equal to population mean. And every time the sampling distribution variance will approach variance of the population divided by n, but will never be equal exactly. Okay, so on an average it approaches normal distribution. That is what we are trying to understand here. So see what we did. We took random number between 1 to 100. How many numbers we took for population? We have taken near about 1000 numbers. So now we are randomly selecting the sample. What is my sample? My sample in the first case, my sample in the first case is from has the size of 35, and this goes from A2 till A37. So actually the sample size is 36. So A2 till A37, sample size is 36. Okay. What I took the first 36 samples. So the sample size is greater than 30. Then for the second, I took the sample from A3 till A38. Now you would say you are not choosing the random sample. Correct. I'm not choosing the random sample. I'm very near to the random sample because all the numbers that has been generated is random. So as I refresh the sheet, you see the numbers are changing. The numbers are changing because I want everything to be random. Yes, definitely it is not 100% random, but I'm trying to achieve the randomness. Okay. So I took the sample mean. These are the sample mean. Okay. So you can understand I can have the sample mean till the point number 965 because the sample size is near about 36. So actually 964. Now then what I did, I calculated the bin for plotting, not required. Then I calculated the frequency of each of the sample and then the probability. And you see I plotted the probability distribution, which is the sample mean and the probability. Now you can see that it is not actually normally distributed. But if you keep on changing the sample, it will approach normal distribution. Sometime it will not, sometime it will approach the normal distribution. But on an average, if you keep on doing this exercise, it will approach normal distribution. This is one. So we talked about approaches normal distribution. Another, we calculated the mean of the population. This is the population mean, 51.44. I said that the sample mean is also equal to, should be equal to the population mean. But see, there is a difference. The difference is of negative 0.265914. But let's take another sample. See now the difference converted from negative to positive and very near to the same amount. So on an average, negative positive cancel out each other. So on an average, the sample mean is going to be the population mean on an average. So approaches normal distribution. Sometime it would be greater than population mean. Sometime it would be lesser than population mean. Got it? Next, we said that the variance, the population variance is going to be the population variance right now is 857.2716, and the sample variance which I just calculated from the sample mean variance, very simple formula, sample mean variance, that's it, that came to 30.66. But the should be variance was variance of the population divided by what? The number of element is 36, so it should be 27. So should be variance is this 22, and the calculated variance of the sample mean is 21. Again, it is not equal. There is a difference of negative 0.43. If the next time you take the samples, it will again negative, then positive, then negative, then positive, then negative. But these two numbers are never gonna be equal. What will happen? It will approach the population variance divided by the sample size. It will approach normal distribution. It will approach population mean. It will approach population variance upon n. So the theorem that we have discussed, the version 2 of central limit theorem, is all about approaching normal distribution. The sample mean distribution approaches normal distribution as you keep on increasing the sample size. Right now, the sample size is 36. If you keep on increasing the sample size and if you add more randomness into this exercise, the probability distribution will approach normal distribution. The mean of the sampling distribution approaches population mean, and the variance of the sample mean will also approaches population variance upon n. Okay, so this is what I wanted to help you understand, that it approaches, it never equal to normal distribution. Okay, on an average, it approaches normal distribution. So with that, I'll end the central limit theorem here. I think we have discussed a lot about central limit theorem, and from the next session, we'll discuss about the prediction that we can do with the help of normal distribution. Thank you. Have a nice day.